In today's lecture, we will come to a conclusion that the CFG and PDA are actually same. Means we all know that this push down automata, whatever the language it generates or whatever the language it understands, is called context free language, and we will see whatever the grammar is used to define this context free language, that is CFG, this thing, and PDA both are same. One is machine, another is the grammar which is used to define the language. Fine. So to begin with this discussion, what we have to do, we have to prove that the following three classes of languages are actually same. That is the context free language, that is the language defined by CFG, the languages that are being accepted by final state by some PDA, and the languages that are accepted by empty stack by some PDA. If you remember, in our previous two lectures we have already proved that these 2 and 3, that is a language which is being accepted by final state in PDA, and the language which is being accepted by empty stack of some PDA, these two are equivalent. We have proven both the way around, right? From we have started with that final state concept, and have appeared to that empty stack concept, and we have also done with the reverse process as well. Right now our job is to show if we can prove that 1 and 3 are equivalent, or 1 and 2 are equivalent, then it is quite we can be quite sure that all these three are equivalent, right? So here in our case we will show that this 1 and 3 are equivalent, because it's easy to prove that whether language is getting accepted by this final state, automatically the stack will become empty. We all know these 2 and 3 are equivalent, nothing to discuss anymore. And so we will just here we will from the concept of CFG we will move to the concept of language is getting accepted by PDA, the final state of PDA, and we will show the reverse process, that whenever language is getting accepted by PDA, then it is also a context free grammar. Fine. Now let us begin with this. Firstly, we will start with the CFG or context free grammar, and we will move to its equivalent PDA. Then we can come to the conclusion that okay, from CFG we can move to a PDA, and then we will see the reverse process. If a PDA is given, how we can generate its corresponding grammar. So if we can prove this two way around, then we can come to the conclusion these two are equivalent thing, right? So given a CFG G, we construct a PDA that simulates a leftmost derivation of G. Now let us focus what a leftmost derivation is. If you just forget about all these technical terms, what is left sentinel form, what is and those, so just let us discuss in some layman's language. If you are having one form written in this manner, small x, capital A, and then alpha. Here we are saying that A or capital A is a leftmost variable. What is the meaning of it? Here we are just depicting in this fashion. We are considering this small x consists of some terminals. Say we are having a string named W, right? So whenever we are into the process, the PDA is going to work like this fashion. It will consume the first input, the rest remains. Then it will consume the second input, the rest remains. So whatever the inputs are being consumed by PDA already, that is being included under X, right? So X is nothing but these are the set of terminals being consumed by PDA already. Now why A is a leftmost variable? If you just see this one, which one is the variable that is lying at the leftmost end of this form? That is A, obviously, capital A. Why? Because alpha, we have already learned that alpha can be it is a string. It can consist of both terminals, it can consist of variables, it can be only terminal, it can be only variable, it can be a combination of two, anything. Alpha can be anything. It's in general we can say it's a combination of terminal and variable. There may be the scenario that there are no more variable is present, no more terminals are present, only variables are there, whatever it can be, but in general we will consider alpha consists of both the terminals and variables, right? So here, if using this fact, we can say that capital A is a leftmost variable in this form. So small x consists of few terminals that are already being consumed by PDA. A is a starting with, if we move from left to right, so we are finding that A is the first variable we have appeared, right? And alpha consists of the rest of the part. It can be anything, terminal, variable, combination of two, right? Then we call this A followed by alpha, the tail of this left sentinel form, right? So why this is why we are saying this leftmost derivation or left sentinel form? Leftmost derivation means how can we derive? Derivation means in place of any variable present in this form, we will replace that variable using other variables or some terminals followed by the production rules, whatever my machine is following in this situation, right? So here our job will be to replace this A with some terminals or with some variables. So we are deriving with respect to A. That's why it is the term leftmost derivation, right? Fine. So if a left sentinel form consists of only terminals, then its tail is epsilon, because here if it only consists of terminals, so x is enough to hold it, means it consists of only terminals, no variable is there. So here no concept of A followed by alpha will be there if this production rule is of only set of only terminals, right? So then we consider the tail as a epsilon part. But the idea behind the construction of a PDA from a grammar is to have the PDA simulate the sequence of left sentinel forms that a grammar uses to generate a given terminal string W. We will see in our example, whenever we move to the example, the concept will be more clearer to you, that if a grammar is given, if we have to construct the PDA corresponding to that grammar, so we have to form this left sentinel form, because left sentinel form is having an advantage that okay, some terminals will be there, and after that whatever the first variable we are encountering, we will keep on deriving it, right? So we can follow leftmost derivation and can gradually move to the construction of PDA following this pattern. Okay, next, the tail of this sentinel form x A alpha appears on the stack with A at the top, right? Because here I have already told you that x are the set of those terminals which are already being consumed. So here at the top most part of the stack, obviously A will be there, right? Because next symbol what we have to do, or what we have to pop from stack, and we have to move according to the production rules given, that is nothing but A, right? So at that time x will be represented by our having consumed x from the input, leaving whatever W follows its prefix x. I have already told you this. If we can more precisely, if we can write the total string as depict the total string using W, we can replace W with xy, because just x part has been consumed and y we are having with us, we have to work on it, right? So this x part is being consumed. So if we push this part or process this part using a stack, then x is being totally consumed, and A is now the variable we need to process, we need to work on it. So here A will be at the top of the stack. Fine. Now if we use this ID notation to denote, we have already learned in our previous lectures that what is an ID, that is instantaneous definition of a PDA, that is, this is the state, y q is our state, and y is the whatever the stack symbol we have to work on it, and A alpha is a remaining set of strings which we need to process, right? So if we follow this ID pattern, and then we need to, as we have already seen our previous slide that A is our top symbol now, so we have to expand A, right? And let us guess that we are having a production, say A is moving to beta, this production is given, so our next job will be to do what? We have to replace A with beta. There is nothing new in it, so my new ID will be like QY, and we have replaced A with beta and beta alpha. Now the question is that what beta consists of? Beta can again consist of a set of terminals and set of variables as well. So we have to find out what is the next most leftmost variable is there, then we can move accordingly, right? And here we are concentrating on only one state Q for the sake of simplicity. It is also applicable for more than one states, nothing to worry. Okay, now this we are having this one QY beta alpha. This may not be a representation of the next left sentinel form because it may have prefix of terminals, right? And so we have to work on it, how to represent it in the form of left sentinel form. In fact, may have no variables at all, and alpha may have a prefix of terminals. So whatever the different situations can arise, this has been written here, nothing else. Now next, so if this kind of situation happens, what can be the way out? How can we move further? Then whatever terminals appear at the beginning of beta alpha need to be removed to expose the next variable at the top of the stack. It's very because with the help of terminal we can't do anything else, right? If we are having only the terminals, our job is to empty the stack, nothing else, because terminal cannot substitute any other values, means we cannot work on it, right? So if any terminals appear at the beginning of beta alpha, then we have to keep it under X or move it off or pop it off so that the first variable appears at the top of the stack. So we can again keep on moving, and these terminals are compared against the next input symbol to make sure our guesses at the leftmost derivation of the input string W are correct, because whatever the terminals we are encountering, means whatever the terminals we are removing, obviously we have to compare it with the W, right? So if you remember whatever we have discussed previously, that we have divided W into two parts, that is X and Y. X are the set of those terminals which are being consumed by PDA, and Y are the set of terminals, remaining terminals, right? So if we are popping some or removing some terminals from this beta part to get the first variable or to encounter the first variable so that we can work on it, so we need to compare whatever terminals we are removing, we need to compare whether it is getting matched with the remaining part of W, that is Y, right? If it does not matches, that we are in a wrong path, we have to discard it off and move to another path, right? So if it matches, then only we can stay in this path, means we are in the right track, otherwise that string will not get accepted by PDA, right? So this thing we have to keep in mind. Then if we succeed in this way, then we will eventually reach the left sentinel form of W, right? Similar way in which we begin our process, means it will be with X, then one variable will come, and then rest part is will be with alpha. Okay, at that point all the symbols on the stack have either been expanded, that is if their variables are matched against the input, if they are terminals. I have already discussed on this. If the stack is empty and we accept by empty stack, if no more variable present, and in search of variable we have already popped off all the terminals present, and we have if we guess that we are in the right track, that means whatever terminals we have popped off, that already gets matched to the string given, that is W. So we are in the right path. Now if no more variable are there, so if we search for the variable, no, we cannot find any more variable, right? So a situation will come when we will find that my stack is empty, right? So we can conclude that the second procedure, that this string has got accepted by the process of emptying the stack, right? Fine. So here whatever informal discussions we have made till now, it can be formally represented like this. So we all know this is a grammar representation. V as a set of variables, T as a set of terminals, Q as a set of states present, and S is start symbol, right? And we'll construct, if we go to the formal definition how it looks like, we will see it. Say we are having one PDA, namely P. It is having only one state Q, then set of terminals are there, and then these are the set of our variables and terminals. Delta is your transition function, Q is your starting state, and S are the again here S is another start symbol, right? So here, if how it is working, so if you remember this one, the ID form, right? So if we begin with this one, we are having one state Q, then we are having this epsilon, the string to process remains is epsilon, and a variable we have encountered is A. And if you follow that, we used a production rule, namely A generates beta. So we are doing nothing but we are replacing A with beta, and just see, it will change to Q comma beta, since the string we have processed is epsilon, so nothing remains with it, just A is being replaced by beta. Fine. Now if for each terminal, what I told you already, whenever we will encounter any terminal, our job will be to pop it off. We cannot expand it anymore. So if you see the second point, that for each terminal, if Q is a state and we have already processed this we are processing a terminal A, and A is there, so whatever, how many number of A comes, whatever the terminal comes, we will pop it off, and ultimately the stack content will be empty. That's why Q comma epsilon is written. Okay, next, if you see one example, we are given one grammar, this one GVTRS, and V is S, T are the set of terminals, this one, and R are the production rules given by this, and it is generating the language string, then a variable namely C, and followed by the reverse of it, right? And W is a combination of A and B. Okay, so here how can we what can be the transition functions? It has already been written in that production rule part. So if you follow the previous two rules, whatever we have discussed in the previous slide, so firstly, if we are having one empty string to, if you concentrate on point A, if we are having one empty string to process, and or start symbol, we are starting with S, right? Then if you follow that the production rules, what it is going to do, it can either from S, whenever we are starting with at the initial part, so it can generate ASA or BSB or C. So that is being written, right? So if we start from the beginning, so it Q can generate ASA, or Q can generate BSB, or Q can generate C, right? Now if we have encountered only terminals, it can be, here the terminal can be A, here the terminal can be B or C. So whatever we have discussed, whenever we will encounter only terminals, not variables, we will just pop it off and empty the stack. It is doing the same thing. Whenever the ID is QAA, then it will give an output of Q epsilon. If it is BB, it will give the same thing. If it is CC, it will give the same thing. Okay, now one theorem is there. The proof is not important, so I have left it for your turn, right? You can follow the book which we are following. There the proof is given, but we all know this one, because the same theorem, that is, when whatever the PDA is being getting accepted by empty string, emptying the stack concept, it is also the context-free grammar, right? If you want to go to details, if you want to learn the proof, you can follow the book from to learn the proof from there. Okay, we'll see one more example. Here these two production rules are given, So you can easily see that what are the set of input symbols. It can be 8, B, it can be 0, it can be 1, it can be opening bracket, it can be closing bracket, it can be plus, it can be multiplication, and these are given. So now we have to define the transition functions, right? Okay, just remember this one, we need to use it off. Okay, firstly we will, here we are having two terminals instead of two variables instead of one is I, another is E, so we will write in respect of both. Firstly we are starting with I. If we start with I, so the total number of terminals already being consumed is epsilon, so starting ID will be Q epsilon followed by I. So what are the production rules present in case of I? If you follow the previous slide, I can produce A, I can produce B, I can produce IA, I can produce IB, again I0 and I1. So this has been written. These are the production rules, right? We can replace with this number of things. Similarly, if you follow the production rules of E, it is very easily understandable. You can just put it off. Now, what are the different terminals present? One is A, another is B, one is 0, 1, opening bracket, closing bracket, plus multiplication, right? So for all the set of all these terminals, our output will be only one thing, that is Q followed by epsilon, because whenever we will see terminals, we will pop it off. You can follow the rules and can do it. It's very easy. Okay, now we will see another example. Here we are given this grammar, that is S generates 0 BB, B generates 0S, 1S or 0. What are the variables present here? S and B. And what are the terminals present here? 0 and 1. So we will construct PDA, right? And I have left it for you. You can just try it off your own. I think you can do it off, right? So we have already seen in our previous examples that we were given these production rules and we have defined a transition function. Similarly, you can do it of your own. I have already solved two examples and I have kept this for you. Okay, next we will see the reverse process. Until now we were given CFG, that is grammar, and we have constructed PDA from it. Here we will do the reverse one. We will be given PDA and we will construct our grammar, right? The construction of an equivalent grammar uses variables, each of which represent an event consisting of, what can be the events? The net popping of some symbol X from the stack, a change in state from some P at the beginning to Q when X has finally been replaced by epsilon on the stack. So we have to just see what are the transitions are if we are popping any symbol from the stack or the PDA, and if it is changing for some input, that is from one state P, it is moving to Q, and whenever whether we have already consumed all the symbols of X and it is being replaced by epsilon. We have to follow all these things to construct the corresponding grammar. Okay, now if this is the PDA defined by this and there is a context-free grammar G such that this one LG equals to NP, that is being is this grammar and the concept of the PDA getting accepted by empty stack are equivalent, then we can construct means then the grammar exists, right? So how can we construct the grammar? Here the special symbol is, it is the start symbol, and all the symbols of the form P, X, Q, where P and Q are the states in Q and X is the stack symbol in tau. So these two approach we have to follow. We will see an example and the concept will be much more clearer to you, right? Okay, so just see the rules first. What can be the productions of G? Right, first production can be for all states P, G has the production of this form. Of this form means what? For if you remember, initial part of PDA is to just push Z0 into the PDA to initiate, right? So Z0 is the marker that we have. First our job is to put Z0 into the stack to make aware that we have begun with our operation, right? So first transition can be this one, right? So if you just follow the previous lecture, I'm not going to the details again. So here just see the transition rule or the replacement, how it is doing. Q naught is our starting state, W is the unprocessed string symbols, and Z naught is the beginning of the stack. So we can move ultimately after many number of steps. What we will do, will ultimately move to the final state, namely P. There will nothing will remain with W. We will just process all the strings, all the terminals present in the string, and Z naught means the stack content will become empty. So after many number of steps, we will ultimately move to this one. This has been written. Okay. Next, if the condition is like this, that my transition function is like this, QAX, right? So how can you do if A is either a symbol in sigma or A equals to epsilon? This can be two situation, and K. How can we ultimately reach to our goal? Means we will follow many number of steps, many number of productions, whatever it is being given, we will move to different states and ultimately we will reach to our goal. So it has been shown here like this. See, firstly we are beginning with the state Q. We have X process to do, and we have to move to, ultimately we have to move to state R K. So how can you move? You have to process the symbol A. So by processing symbol A, say we are moving to, from this state we are moving to R, and we are having the stack symbol Y1 with us now, then ultimately we can move to R1. Then again from R1, say we are having stack symbol Y2, we can move to R2. So these are the sequence of steps. If you divide it one after another, these are the different movements we are moving to reach to our goal. Okay. This production says that one way to pop X and go from one state Q to the state RK is to read A. Just the explanation of the previous thing, whatever I told you, it has been written and we have already discussed many number of times. Just go through it. I think it will be clearer to you. Or just popping one thing and moving to the other state, stack content getting changed, and so on so forth. Right. Now we will just see the example. Say we are given this one PDA, right, and we have to construct the grammar. So we will see how to just generate the production rules, right? So just remember these transitions and we will write the production rules. If you see this one, okay, so it is saying that first with the start symbol, what will be my content? Just note down one thing. Instead of Z naught, we are using Z here. Do not worry, if you wish to use Z naught, you can do it. So my start symbol's job is to, it will be at the same state and at Q, and it will just push Z into it, right? So our beginning is from this one. Now let us just consume one after another. Just remember the previous diagram. We will process all the transitions which are written in green first, then we will focus on the concept of terminals only. Okay, firstly, so we will focus on the part of variable. So we will work with the green, 4 green transitions have been written with green ink, that we will focus on it. Okay, so first what we are doing, say if we are fed with 0, just remember we are having QZQ with us, right? So we are feeding 0 to it. So if you just consult the previous diagram, you can see that for 0 and Z with it, it will generate the output, right? It has been written in bracket, since that this transition Q0Z, for this transitions our output is QAZ, right? So you can see here, so if we are feeding 0 with this application QAQ, so ultimately we can move to QZQ, because this will be replaced by AZ, Q right? So for this transition q0z, we can come to we will generate this az. If you similarly see that if we are feeding 1 to it, it will instead of moving to a, it will move to b. So this has been written, right? Same again, if we are these were with the starting symbol, that is z. Now if we are at this one, that we are starting with a, state a, and we are having 0 to it. If you remember this transition for q0a, it will be at the state a only. So just see, it is with the state a, right? So a is there, and similarly for 1 at b, it will be at b. Now let us come to 3 operations given with respect to terminals that are being written here. If we are just at aq, if we are having one terminal, it will generate only 1. Just see that whenever we are having 1 to consume and we are at a, then if it does not generates b again, at a there is no transition for 1 is given. So if 1 is being encountered at a, it will just pop off. That's why the transition is q comma epsilon, right? So it will generate 1. Again at b, it will generate 0, and if at z it gets this symbol empty string, if the string is totally empty, then first transition will be null only, right? So this has been written very clearly here. So if you can generate this transition rules, so you can generate the grammar as well. Okay, so that is the way out, and this much for today's class. And in the next class we will see this very important concept, what are useless symbol, what is epsilon production, and what are unit productions, and why we need to eliminate those from CFG and all. Okay, thank you.